Hello everyone, my name is Xuan, and today I'll be talking about developing secure smart contracts through a runtime monitoring approach. What are smart contracts? Smart contracts are executable code with explicit instructions on establishing compliance. This meant that smart contracts are autonomous and does not require trust to be placed on a third party. Smart contracts are deployed on a blockchain, which makes it decentralized, immutable, and traceable. The purpose of smart contracts, also known as a decentralized application, is to enforce a safe method of monetary, assets, and digital rights exchange between the entities involved. Smart contracts are built on top of Ethereum using a Turing-complete language called Solidity. Smart contracts are rapidly gaining popularity across the wide span of industries due to its features. Yet, it is a great challenge in ensuring the correctness of code in Turing-complete specification languages. This undermines the trustworthiness of the smart contracts. One of the notable hacks in the history of Ethereum is the DAO attack, which arises as a result of a logic error. The DAO, short for the Decentralized Autonomous Organization, was an organization founded for the purpose of crowdfunding and is fully automated and decentralized, equivalent to the decentralized form of Kickstarter. The developers intended for the decentralized application to prevent any tampering or misuse of the investors' funds through the Ethereum platform. Investors would be able to send money in the form of Ether and be awarded tokens which gave them voting rights on possible projects. Investors are also able to withdraw their rewards from their investments. However, the ability to withdraw the investors' rewards turns out to be a vulnerability of the decentralized application that was eventually exploited by a hacker to withdraw 3.5 million worth of Ether from the Decentralized Autonomous Organization. Vultron is an integrated solution comprising of the Go Ethereum virtual machine and Solidity compiler. Vultron seeks to detect and mitigate vulnerabilities in smart contracts by monitoring the state of the contract during its execution. This is done through the insertion of additional custom debugging instructions. In Ethereum, gas has to be paid for the computation and execution of instructions and is proportional to the operations performed. Having additional instructions will lead to more operations to be performed, which in turn consumes more gas and ultimately affect the execution of a contract itself. Therefore, the gas instrumentation of Ethereum has to be manipulated to allow the debugging instructions to be executed at no cost. Since the execution of smart contract is by the Go Ethereum virtual machine, we need to modify it such that it can recognize a sequence of bytecodes for the debugging instructions and execute them at no cost. However, editing the bytecode directly for the Ethereum virtual machine to execute is a low-level task and is not easy to perform. As such, we also modify the Solidity compiler such that gas manipulating instructions can be added through inline assembly code. With that, debugging instructions can be inserted to track the state of a contract and to modify its execution dynamically during runtime. How will Vultron help in the development of a secure smart contract? Firstly, Vultron will check for vulnerabilities during runtime which can decode issues that would not be easily detected through a static approach. Vultron ensures that each detected vulnerability can be exploited and does not generate false positives or false negatives. Secondly, Vultron is also informative as it can provide details about the state of the contract and its execution. This allows for developers to replicate the exploit and determine the root cause of the exploit. Last but not least, Vultron is also a generic solution. Vultron is not limited in its detection capabilities to a specific set of vulnerabilities, nor is it restricted by the number of known attack patterns. Vultron is versatile and can detect any inconsistencies in the contract. To demonstrate the use of Vultron, we look at a simple contract that adds the value of two parameters and returns the result to the function call. This function is subjected to an integer overflow for decimal values greater than 255. To catch runtime errors like this, we first insert gas manipulating instructions to disable the Ethereum gas consumption for the debugging statements. Thereafter, the debugging instructions are added into the function to determine the validity of the state that is to be transitioned to. Finally, we revert the configuration of the Ethereum virtual machine to consume gas for the normal instructions. Through this, we have successfully created a block where debugging instructions can be added without consuming gas for its execution. The contract can then be compiled by the compiler and deployed using the Ethereum virtual machine. This allows us to perform runtime monitoring and dynamically alter the execution flow of the program. Therefore, through the use of Vultron to detect and mitigate vulnerabilities during runtime, we hope to advance towards secure smart contracts. Thank you.